Okay, now can you see the screen that I'm sharing?
Okay, it is clear. You can
Okay.
start.
Can you see the mouse is moving right now?
Yes, of course.
Okay. Okay, hello everyone. Good afternoon and good evening from my area. My name is Muhammad Shiddiq Fizuhri. I'm from University of Indonesia. And for today, I would like to presentate my research about charged neutron star stability against radial pulsation. Okay, let me start the presentation. Okay, this is the outline of my presentation. Okay, first, let's start with the introduction. Neutron stars. Stars are born from a massive collection of gas and dust in space or from a nebulae. Gravity then pulled those gases and dust together. More and more gas and dust being pulled by gravity. As the gas and dust came together, the center of it gets hotter. A star then are formed when the core gets hot enough for a nuclear reaction. Gravity pulled the mass of the star and forced a nuclear fusion, while the fusion reaction energy pushes against gravity. Then hydrogen in the core of the star fuses into helium, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. And once the core reaches into iron, it stops fusioning because iron itself is a nuclear ash. A neutron star is born from a collapsed massive stars. The pressure of the collapsing star is so great that it fuses proton and electron into neutron. Hence, the name of the star is a neutron star. On this research, we study the effects of electromagnetic force of a neutron star because neutron stars are usually considered neutral. First, we study the Tov equation. The Tov itself stands for Tolman-Oppenheimer-Volkoff equation. And because we introduced an electromagnetic field, thus it's now a modified Tov equation. First, we start from a Schwarzschild metric equation, equation number 1, in which nu and lambda is a metric function of r and t, space and time. However, r itself is a function of t, so the space itself is a function of time. To modify a Tov equation, we add an electric field on the energy momentum tensor. The modified part is written with red in the second equation. Next, the metric coefficient now equals to the equation number 3, and the red part is the new and modified part. Now we obtain the modified Tov equation, equation number 4 through number 6. And the equation number 6 is the newest and the modified part of the Tov equation. Now we have a rho charge, which is the distribution of charge density. We modeled the functions such as for a decreasing charge density across the radius, equation number 7. And for an increasing charge density across the radius, we have equation number 8, in which rho charge 0 is greater, it's less than rho charge 0. From the energy momentum tensor before, we obtain equation number 9 until 12, in which the red part is the new and modified part from Tolman-Oppenheimer-Volkoff. These equations are used to calculate the stability of the modified Tov equation. And now we have the pulsation equation, equation number 13, and this red part is also the new and modified part. And this pulsation equation is the stability of the modified TOV equation. Now, our MF model. Our MF itself is relativistic mean field model. Now we can write the Lagrangian density for this model as equation number 14, in which Lagrangian baryonic, lepton, and bosons are equation number 15, 16, and 17. Now the Lagrangian density for each bosons are equation 18 to equation 22, in which equation 22 is Lagrangian gamma. This is for the electromagnetic force. Next, from the definition above, now we will obtain the Lagrangian density for the relativistic mean field model as equation number 23. And now we have the red parts as the new part from the modified TOV equation. Hence, the energy density and pressure equation inside the neutron star will be calculated as, this is the energy density, equation number 24, in which this red part is the new modified part, and the pressure, equation number 25, also has a red part, which is a new and modified part from the modified TOV equation. In general, the chemical potential equilibrium of a neutron star is written as equation number 26 to 28. Now with the chemical potential for each field on a charged star, equation number 29 to equation 31, in which in equation 30 we have the new modified part. And for lepton density, we obtain equation 32, and for proton density, we obtain equation number 33. And now, let us discuss the result of my study. Okay, on this experiment, we use 4 types of variation. We use 2 values of rho charge 0 and also 2 values of n variable. For rho charge 0, they are 0.5 times rho 0 and 0.99 times rho 0. And also for n, they are 1 and 2. In this figure, there's a graph that shows the relationship between the energy density and the pressure of a neutron star. While the pressure is at maximum 674.82 mega electron volts per femtometer cube, we obtain that the energy density without an electric field are 1727.9 mega electron volts per femtometer cube. Now, this graph shows the relationship between energy density and the pressure of a neutron star with a decreasing rho charge. We can see from this graph that the biggest difference given by the decreasing rho charge, rho charge 0 equals 0.5 times rho 0 and n equals 2. Also from this graph, we can see that the n variable causes the pressure to drop. And also, the equation of state gave an inconsistent shape of the star. Next, we have a graph that showed the relationship between energy density and the pressure of a neutron star with an increasing rho charge. Now we can see that the biggest difference was given by a rho charge increase, with rho charge 0 equals to 0.99 times rho 0 and n equals 1. Just like before, the n variable causes the pressure to rise, but the EOS equation gave a consistent shape of the neutron star. Okay, next. Now we have a graph that shows us the relationship between the charge density and the pressure of a neutron star. On this graph, only the maximum difference between the decrease and increase are shown. And also we use the logarithmic in the y scale, so it's easier to see. Now we have a graph that shows us the relationship between charge density and the pressure of a neutron star with a decreasing rho charge. As we can see from this graph, the rho charge 0 equals 0.5 rho 0, always lower than the rho charge 0 equals 0.99 times rho 0. And also the n equals 2 is always higher than n equals 1. While on this graph shows us the relationship between charge density and the pressure of a neutron star with an increasing rho charge. We can see from this graph that rho charge 0 equals 0.5 times rho 0 is always lower than the rho charge 0 equals 0.99 times rho 0. Unlike the decreasing counterpart, the n equals 2 is always lower than n equals 1. Now, we have a graph that shows us a relationship between charge density and the radius of a neutron star. On the next graph, we have a relationship between charge distribution and the radius of a neutron star. Next, we might discuss the neutron star stability. On this part, we will show the numerical calculation result of the neutron star pulsation, where we will see the neutron star stability point. The mass at omega 0 squared equals 0 are a turning point of a neutron star stability and instability. A star is considered stable if the eigenvalue is positive and not negative. Now we can see from this graph that this is a comparison between the eigenmass rho charge equals 0 with an increasing rho charge. We can see from this graph by giving the star a charge, the maximum mass of a star is shifted. As you can see from this zoom in, you can see that the star is growing. From the biggest shift, we can see that the change of the pressure also causes the change on the mass of the star. Next, we can see on this graph also showing a comparison between the eigenmass rho charge 0 with a decreasing rho charge. Unlike the increasing counterpart, the decreasing rho charge gave an inconsistent shape of a star because now we have two biggest different shifts, one on the lower side and one on the bigger side. Next, this graph shows us the comparison between neutron star mass and radius. And lastly, this is a graph that shows us the comparison between the neutron star mass and the core energy density. And finally, this is the table that shows us the neutron star stability and equilibrity and stability configuration table. This is the numerical result of the graph that has been shown. Conclusion. There are no significant difference between rho charge equals 0, increasing rho charge, and even decreasing rho charge. However, if we compare the mass between the increasing rho charge and the decreasing rho charge with the mass of the rho charge equals 0, we will see that there is a mass difference. There is a difference between the neutron star radius if we compare between the two configurations, the maximum equilibrity and the omega 0 squared equals 0 stability. The radius of the n equals 2 is always smaller than the n equals 1. However, the core energy density is higher on the n equals 2 than n equals 1. There are differences between the two configurations, the maximum equilibrity and the omega 0 squared equals 0 stability. The smaller the radius of a neutron star, the higher the core energy density it will become. The smallest radius, 10.4633 kilometers, is given on the maximum equilibrity configuration, while on the omega 0 squared equals 0 stability configuration, the smallest radius is given by 10.4693 kilometers. On the other hand, the biggest radius, 11.0522 kilometer, is given on the maximum equilibrity configuration, while on the omega 0 squared equals 0 stability configuration, the biggest radius is given by 11.0369 kilometers. And finally, a neutron star with an increasing rho charge are far more stable and consistent than a neutron star with a decreasing rho charge. And that's all for my presentation for today. Thank you for your attention.